Okay, yeah, thank you very much. So let me also first thank the organizers for the invitation to this very interesting conference. It's really a pity that I was not able to join in person, but I'm happy that I can at least participate online and join this interesting conference. I really enjoyed already the old talks so far. So in my tutorial, I would like to give you a basic introduction into tensor networks. I will mostly focus on the methods themselves to give you an idea what they are about. So they really have become one of the most powerful tools to study strongly correlated systems, and particularly also frustrated magnets. And then I will also show you some applications very briefly, and then also some recent developments. Okay, and please don't hesitate to interrupt me at any time. So I'm happy to discuss also details if you have further questions. But let's start with a kind of general motivation, right? We all know that one of the grand challenges we face is to understand the emergent phenomena and strongly correlated systems, with famous examples like high-TC superconductivity or various magnetic phenomena or quantum spin liquids in frustrated magnetism, so particularly relevant for this conference. Or then there are also many new emergent phenomena, new states of matter that can be realized, for example, with ultra-cold atoms. Now, studying these systems or the models describing these phenomena is typically very challenging, because typically there's no exact analytical solution, and the standard analytical approaches like mean field or perturbation theory typically fail here, so that in practice often accurate and efficient numerical simulations are essential if you want to get insights here. Now, one of the state-of-the-art approaches for many body problems is quantum Monte Carlo, where the main idea is to sample this exponentially large configuration space statistically, right? So that in the end, you manage to get a computational cost, which is polynomial in system size and not exponential. So this is really very powerful for many spin bosonic systems. So take, for example, the 2D square lattice Heisenberg model, where we well known that the ground state has nil order. If you look at this state-of-the-art study by Stanwyck and Everts, they went up to system sizes of 256 squared, which corresponds to a huge Hilbert space, but with quantum Monte Carlo, this is possible. And then they extracted, the sublattice magnetization here up to very high precision, right? So it's really amazing what you can do with quantum Monte Carlo if it works. However, there's this huge but here, namely it fails for important classes of models, namely for fermionic systems and also frustrated spin systems. And this is due to what is called the negative sign problem in quantum Monte Carlo. So I will not go into the details here, but what it implies in the end is that simulation time scales again exponentially with system size and inverse temperature, which means that you cannot really access low temperature properties for large systems for these problems, right? So this the negative sign problem can be seen as one of the biggest problems in computational physics, and in the end also the reason why there are still many important problems which are unsolved. So if you want to make progress, it's really important to come up with new accurate tools with which we can address these problems, which don't suffer from this negative sign problem. And over the past decades, there has been a very nice progress with a broad range of different approaches. So this is not a complete list. And all these approaches in the end come with their own advantages and disadvantages, right? So we are not at the stage where there's just one magic black box method that could solve everything. But it's interesting that over the years, all these methods have become more and more accurate, such that they also start producing overlapping and consistent results, right? And I think that's great progress in computational physics, that we can now address some of these most challenging problems, also in frustrated magnetism. And now among the most powerful family of methods are tensor networks, and that's what this tutorial is going to be about. So these tensor networks have already been extremely successful for the simulation of one-dimensional systems, and this is mostly thanks to the well-known DMRG method, the density matrix renormalization group, which was invented by Steve White 30 years ago. And DMRG is actually an underlying variational ansatz, a variational tensor network ansatz, which is called the matrix product state. So I will explain you later what this picture actually means. But then there are also there are also different tensor networks than matrix product states. For example, this MIRA here, the multi-scale entanglement renormalization ansatz, which is a powerful ansatz for critical systems in one dimensions. And then there exist also the generalizations of these tensor networks to higher dimensions called the PEPs or the 2D MIRA. And of course, the goal here is to repeat this enormous success of one-dimensional tensor networks in higher dimensions. Now, the problem is that the involved algorithms here in higher dimensions are more challenging than in one dimension. And that's in the end also the reason why it took actually quite many years to come up with, practical, efficient algorithms. But in the past 5-10 years, let's say, there was a lot of progress, and also these 2D tensor networks have become a very powerful and versatile tool to study 2D systems. Okay, so I will, in my talk, start with a basic introduction, but then also tell you a bit more about these higher dimensional tensor networks and what they can do. Okay, so here's the outline of the lecture. So I will really start with a basic introduction to tensor networks. I will show you this, what this diagrammatic notation is about. And then the main idea of a tensor network ansatz, which is closely related to what is called the area law of the entanglement entropy. Then we will see different examples of tensor networks, and we will see that one way to classify these tensor networks is by the amount of entanglement entropy they can produce. So what sort of entanglement scaling they can reproduce. And then I will also go a bit into the details of the contraction and optimization of tensor networks. Okay, and then in this part here, I will very briefly flash some application examples. So this talk is not so much going to be about applications. I will tell you about several recent applications in my tomorrow's talk on strontium copper borate. So I will also refer to that a bit. And then in the third part, I would like to tell you about more recent developments with 2D tensor networks. So like, for example, extensions to finite temperature or the computation of excitations, or recently we also made progress in pushing tensor networks to 3 dimensions. So I would like to highlight a few of these directions. Okay, so again, if you have questions, just don't hesitate to interrupt me. Okay, so let's introduce this diagrammatic notation, which is commonly used in tensor network algorithms and which really simplifies the discussion a lot. It can also be seen as a kind of a new language to think and talk about quantum many-body problems. So the basic objects we're dealing with are tensors. So you can just think of these as multidimensional arrays, right? So an object with a certain number of indices. And we now graphically represent this by a tensor by a shape. So here a sphere, for example, and then the legs attached to this shape correspond to these indices, right? So here we have, a tensor or a multidimensional array with 3 indices, so 3 legs. Here would be a tensor with 4 legs, here with 2 legs, and that's, of course, that's nothing but a matrix. Then this with 1 leg would be a vector. And then if there's no leg attached to it, this is simply a number. And now there's one basic rule that you need to know, namely whenever you connect 2 tensors together, what this means is that we take the sum over this joint index, right? So what this represents is nothing but the matrix M times the vector V, where we take the sum over this connected index J, and this results in a new vector, which we call U, right? Okay, so here are some other examples. So that would represent a vector times a matrix times a vector. So we take the sum over both I and J, and this results in this number here. So if you take this sum over all these indices, this is what we call the contraction of the tensor network. Or here would be another example, right? So now a bit more complicated with 3 tensors. So we contract the entire network, taking the sum over these 3 indices. And then we are left with the open legs here, right? So whenever you see open legs in a tensor network and you do the contraction, they remain open here, right? So So this is really very useful, especially if we're talking about very complicated tensor networks, right? So here would be an example from the 2D mirror. It does not really matter what it represents, but you see it can get very complicated. And imagine if you would write out this diagram here using sums and formulas, this would be a complete mess, right? And in the network here, you can directly see how the tensors are connected with which legs, right? So this diagrammatic notation is really helping a lot. Okay, so now the main idea of a tensor network ansatz is typically to have an efficient representation of quantum many-body states, and most typically the ground state of some local Hamiltonian. Right?
Hi, Philippe, I have a question.
Yes, please.
So when you say vectors, do I need to worry about the vector space and the dual space, like the bracket notation, and how you contract? How does it show up in this notation? Just to make sure that I can connect it up with quantum mechanics.
Yeah, indeed. So there's no meaning whether if I put these indices on the lower end or the upper end. So there's no convention. It's just a multi-dimensional array to think about it. And then if I show a vector here, it's a priori not clear if this is now showing a bra or a ket. That's a matter of definition. But what you can say is that, so we'll come back to this later. If you show a wave function, then the way to represent the complex conjugate of the wave function is just by its mirror image. So this is the typical thing you do. So it's like the complex conjugate is essentially something that you mirror along an axis. But in the end, there's no convention that you could recognize, is this now a ket or a bra? Some people take the ket for the tensors with legs going down, and some other people do it the other way around. So that's a bit a matter of convention, but this is not something you can read off from the diagram directly. But okay. Thanks for the question.
Okay. Yeah.
Okay, so let's take a lattice here with n sides, where each side is described by some local Hilbert space. So let's just take a spin 1/2 system. So each lattice has dimension 2. Right, so the full Hilbert space lives in the tensor product of all these small Hilbert spaces. So it has dimension 2 to the power of n, so growing exponentially with system size. And then typically we consider a Hamiltonian with local terms, so nearest neighbor, or just with some short range Hamiltonian. So whenever you want to represent the ground state, in general, you need 2 to the power of n coefficients, right? So these are the expansion coefficients in this tensor product basis, right? Where on each side, ik, you go over the 2 possible basis states, spin up and spin down, right? So this is, so you have these 2 to the power of n coefficients. And of course, these are exponentially many numbers, which for certain system size is no longer possible to store on your computer because it's just too big.
Hello. So
yes.
Interaction terms in the Hamiltonian here?
Oh, yeah, yes. So this can be anything. So it can just be interacting, non-interacting, whatever. So hopping interactions, spin interactions. So this is just denoting some general interaction term here between nearest neighbors, but you can also take further ranged interactions. Yes, good questions, thanks. Okay, so for simplicity, let's take a lattice with 6 sides. So we have 2 to the power of 6 coefficients. And now let's use our graphical notation we introduced before, right? So these expansion coefficients can be seen as a multi-dimensional array with 6 indices. So here's our shape, our tensor with these 6 indices. So these 6 legs here corresponding to these 6 indices. And now the idea of a tensor network ansatz is simple, namely we want to decompose this big tensor into smaller pieces, right? As for example, shown here, right? So this collection of tensors connected by lines is in the end what we call a tensor network. Now, to each of these connections here, we can associate a certain Hilbert space, which has a certain dimension d, which is called the bond dimension, right? So it means that this index E runs over d different elements. Now, this particular decomposition, this is nothing but a matrix product state. So a matrix product state has exactly 1 tensor per lattice side, and then they're connected, on a 1-dimensional chain, as shown here. Now we can evaluate this tensor network simply by taking the sum over all these joint indices, right? So that's the rule we mentioned before. So if we take the sum over A, B, C, D, and E, then we obtain a new tensor psi tilde. And the goal is now that psi tilde is an accurate approximation of the exact psi, right? And again, so here we have exponentially many numbers, whereas here in this ansatz, we have a number of parameters which grows only polynomially with D and the number of sides, right? Because if you look at the number of elements of this tensor here, what is it? It's D times 2 here for a spin 1/2 system, right? So every tensor has of the order D squared elements, and here we have n of them. Okay, so this gives you a polynomial number of parameters, and this is what we mean by an efficient representation. But of course, I'm cheating here, right? You should ask, why should this ever be possible, right? In general, it's not possible to replace an exponential number of parameters by a polynomial one. And this is, of course, true. But the thing is that what we're interested in, the states we're interested in are special. So we would like to have a representation of ground states of local Hamiltonians. And if you look at the entire Hilbert space, these occupy only a very tiny region in the Hilbert space. It's also called a small corner of the Hilbert space. And what these states make so special is that they're much less entangled than a general state in the Hilbert space, right? And that's expressed what it's called the area law of the entanglement entropy, which we're going to discuss in the following. But before coming to that, let's consider a simplified problem, right? Let's take our big tensor, and instead of splitting it several times, we can also just split it one time in the middle and then ask ourselves, what's the bond dimension that we need in between here, right? Is it something which is not very large, so then we get away with a certain compression, or is it something that needs to grow exponentially with system size, and then we have not really gained anything, right? That's the question. Now, let's make it even simpler. So instead of having many legs, we can combine all basis states on the left into a left basis, so this L here, and all the right basis states into a right basis R here. So then in the end, what we split is just a matrix, right? We can now split this matrix using a singular value decomposition, so that exists for any matrix. So this splits the matrix into a unitary matrix U, a diagonal matrix S with positive elements, and which are typically sorted in a descending order. And V is also a unitary matrix, right? So we can do this decomposition, and now we can insert this decomposition in the expansion of our wave function. If we do this here, we now have this unitary U, which define a basis transformation on the left basis. So this gives a new basis UK, and then the same we can apply V on the right basis, giving us new basis VK, right? And then we arrive at this form here, and this is nothing but the Schmidt decomposition of the wave function, which you may know from your quantum mechanics course, right? So now instead of having a double sum over left and right basis, we end up with a single sum, sum over K of SKK, and then a left basis state times a right basis state, right? And this K here, so this sum here goes over half of the total basis state, so 2 to the power of n over 2. Okay, now the question is, if you look at this sum here, right? So these SKKs in the end are positive, so you can see them as weights. And the question is a bit, how many terms in this sum here are really relevant, right? So let's have a look at special cases, right? So there's a special case when S11 is 1 and all the other elements are 0. So that would be the case of a product state, right? Where the wave function can be split into the middle, and you can write it as a product between left and right. So there's just one single weight, which is of size 1, and all the other weights disappear. So this would be a product state without entanglement. Here would be an example of a state with entanglement. So imagine if you have 2 coefficients here, which are finite and all the other ones are zero, then you would have a superposition. So this would be a simple example of an entangled state between left and right. In the most extreme case, all the weights would be finite and all of them of equal size. And this would correspond to a maximally entangled state, right? So you have all basis states left and right, which are equally important in this sum. Now the question is, what should we expect now for the states we're interested in? So if you take a random state from the Hilbert space and plot the distribution of SKK, then you essentially obtain a flat distribution, right? So it's close to a maximally entangled state. And it means in the end, well, you know, all the weights here, all the terms appearing in this sum are important. But now if you plot this distribution for a ground state, what you will see is that there's a fast decay here, and there's a tail here where the weights are exponentially suppressed, right? So what you can do then is to keep here this relevant part and cut this part here, which is very small, right? So if you have here a contribution which is 10 to the minus 30, it will not really contribute to this wave function, to the wave function in a significant way, so you can leave it away, right? So that's in the end the idea that we approximate the exact wave function by psi tilde, where we take this sum k here, not over all states, but only up to chi states, let's say, where these weights are large and the other ones will leave away, right? So it means that in the end, we can choose this bond dimension to be equal to this cut of chi, and we still have a good approximation of the wave function. And now, you see here, we have followed a very specific procedure how we can select the basis states on the left and right side, right? You can also choose different basis states, and one can actually show that this choice that we have done here minimizes the norm distance between the two wave functions. So it's an optimal choice of basis states if we want to restrict our basis to a smaller number. And this way of selecting the basis states, this was actually the key idea of the DMRG method, how it was introduced by Steve White 30 years ago, right? So DMRG in the end is differently formulated. It's about how to truncate the Hilbert space, but how to select the relevant basis states is exactly in this way. Except that back then, when DMRG was introduced, the discussion was not based on the single values, but based on the eigenvalues of the reduced density matrix. So this is why it's called the density matrix normalization group. So let me just mention this as well. So the reduced density matrix, so if you have again the system split into an A-B part, we can compute the reduced density matrix of the A side simply by taking this state and tracing out the B side. Now, if we do this for the wave function that we had before, so in this representation here, what we obtain is that, you know, the VKs go away, we trace them out, and what we obtain is the density, the reduced density matrix here in diagonal form, where the lambda k's, the eigenvalues, are equal to skk squared, right? So then this now denotes then the probability with which such a basis state appears on the left side. And then we can do the same argument. So the best way to select the basis states is simply to keep the basis states here which have largest probability, right? So this is equivalent to the discussion we had before. Okay, so now instead of looking at the distribution, we can also introduce a measure of entanglement, right? Which tells us how strongly the two sides are entangled. And the most basic or the most common entanglement measure is the von Neumann entanglement entropy, which is given by minus trace rho A log rho A, or which can be also described here using the eigenvalues of the reduced density matrix. Okay, so if we take the product state from before, in the product state, only lambda 1 is 1 and all the others are 0. So this reduces then to minus 1 log 1, which is 0, right? So a product state gives us naturally a 0 entanglement entropy. On the other extreme, a maximally entangled state. In a maximally entangled state, all the basis states here have equal probability. And if you have m basis states, then the probability of each state is 1 over m. And if you then compute the entanglement entropy, it's log m, right? So in the end, the entanglement entropy is bounded by 0, and log m, where m is the total number of degrees of freedom. Okay, now the key question is now, how large is S in the ground state, or more specifically, how does it scale with system size? So let's take here a 1D system again, and now instead of splitting in the middle, we can also look at the block A here embedded in an infinite system, and then ask what is the entanglement entropy as a function of block length L here in 1 dimension and then here in 2 dimensions. So we will have, then we can ask what's the entanglement entropy, and then the number of relevant states to describe such a region here will then be roughly scaling as the exponential of the entanglement entropy. Now, if you take a random state from a Hilbert space, then the entanglement entropy will be extensive, meaning it will grow with the volume of your region A, so with the number of lattice sites, right? So D is just a spatial dimension here. However, if we now take a ground state of a local Hamiltonian, then they typically obey what's called the area law of the entanglement entropy, which means that the entanglement entropy is proportional to the area of the boundary between A and the rest of the system, right? So here, in 1 dimension, the boundary is 0-dimensional, so which means that the entanglement entropy will become a constant. Well, so this is asymptotically true once L becomes larger than the correlation length. Or here in 2 dimension, it means that the entanglement entropy is proportional to the length of the boundary here. Okay, so this is for gapped Hamiltonians. For critical systems, in 1 dimension, there's a correction to this area law. So we have an entanglement entropy growing as log L. So, but that's still a mild violation compared to a volume law. And then some critical states in 2D also have a log L correction. Okay, now you see, a tensor network is not necessarily good ansatz for any state in the Hilbert space. I mean, it's not always efficient for any state in a Hilbert space, but it's designed in such a way that it can reproduce a certain entanglement scaling, right? So that's the basic idea. And then you can then also design different types of tensor network Ansätze that can reproduce different entanglement scaling. Yes, please. Please. I think
you have a question. Someone raised the hand among the online participants.
Yes, please.
Yeah, so these laws for the entanglement entropy, is it an analytically calculated thing, or is this only numerically verified for different systems?
So did you ask for mathematical proofs of it? I didn't hear it.
Yes. All these laws, is there any mathematical proof, or only like numerically verified for different systems?
Yeah, so it's rigorously proven in 1 dimension. In higher dimensions, there's not a rigorous proof yet, as far as I know. But everything that has been found so far, let's say, is that this would, I mean, you know, based on numerics, is that this is holds also for higher dimensional systems. And then, you know, there's also exact models where you can show this. But let's say a rigorous proof in higher dimensions is still lacking. Yeah, thanks for the question. Okay, so then let's go back to our matrix product state. So again, we have 1 tensor per lattice site, and then the accuracy of this matrix product state is controlled by the bond dimension D here, right? And now we can easily see that this matrix product state reproduces the area law in 1 dimension, so a constant entanglement entropy. So why is that? So imagine if we cut the system in the middle and compute the reduced density matrix, the number of eigenvalues that we can obtain will be bounded by D, because D is the number of states we keep. So the entanglement entropy will be bounded by log D, which is a constant independent of L, independent of the block size, right? So it's a constant entropy, but in the end it's fine, because in 1 dimension, the area law also implies that the entanglement entropy will become a constant. Right, and in the end, you see, this in the end is also the reason for the success of DMRG and matrix product states, right? It really means in the end, you can go to very large systems in one dimension, or even infinite systems in one dimension, and you can still get away with a finite number of states that you keep, right? So that's really the magic why DMRG is working so well. Okay, now early on, people also wanted to simulate systems in 2 dimensions using this idea. And the simplest way to do this is to take a matrix product state and putting it on a 2-dimensional lattice with a snake, as shown here, right? So in the end, this boils down in mapping your 2-dimensional system onto a 1-dimensional system with long-range interactions. So this you can do. However, there's one issue now. If we look at the entanglement entropy, so imagine if you make a cut here, then we know that the area law in 2 dimensions implies that the entanglement entropy will grow linearly with the cut length here, which in the end means that the bond dimension has to grow exponentially with this length here, right? And the reason in the end is that if you look at the left and the right side, there's only one connection connecting left and right. So this bond here has to carry the entire entanglement between the left and the right. And if you increase the system size, you have to increase the bond dimension exponentially accordingly. So this still works if this length here is not too large, right? And we're talking about, like 2D systems of maybe 8, 10, or 12 sides, so which is already quite large with nowadays computations. And actually, this is one of the very successful approaches that many people use to investigate physics of 2D systems, right? So you're just limited in this size here, but not in the other length. So that's why then people typically use cylinder calculations, because this length here is the cheap one, and this one here is the exponentially increasing one in computational cost. Okay, so you can do this, but you're limited in the system size. And now, in order to solve this, we have to use a true 2D tensor network ansatz, and the solution is simple, namely we just introduce more connections between the tensors, right? And this leads us then to this PEPS, or projected entangled pair state, or also called tensor product state, and which can really be seen as a natural generalization of MPS to 2 dimensions, right? We also have one tensor per lattice side, and each tensor is connected to its nearest neighbor. And now this ansatz here very naturally reproduces an area law in 2 dimensions, right? So imagine now if we make a cut through the system, then what you can observe is that the length of the cut is equal to the number of bonds you cut. And now if each bond can contribute log D to the entanglement entropy, what you end up with is an entanglement entropy which is bounded by L times log D, right? Which is something which scales linearly in L, which is the area law in 2D, right? Another way to see it is to simply, group all tensors together on the left side, all tensors on the right side, and group all these indices together. So this results in this tensor network here with a thick bond dimension of D to the power of L. And then again, the bound on the entanglement entropy will be log of this. So this is equal to L times log D and proportional to L, right? So this is how you can see it. Okay, so this is now an ansatz that you can use for finite systems that you can scale up to larger and larger systems. And now there's also a special ansatz with which you can directly target wave functions in the thermodynamic limit, right? And that's called an infinite PEPS or IPEPS. And the advantage here is that there's no finite size and boundary effects here. Now, if your wave function is translational invariant, the way to parameterize it is simply by one tensor A that you repeat on your lattice. Okay, but since we are working in the thermodynamic limit here, translation symmetries can also be spontaneously broken, right? If you think of a nil state, then you need 2 tensors, one for each sublattice, right? So this could be represented by this ansatz. Or more generally, if you have a more complicated symmetry breaking pattern, you can just use a larger unit cell of tensors, which is repeated on the lattice. Now, of course, typically you don't know the right unit cell in advance. So what you do in practice is to just run simulations then with different unit cell sizes and then check which unit cell gives you the lowest variational energy, and this then really corresponds to the true ground state. Okay, so that's IPEPs. And now there's another class of tensor networks, which could be called hierarchical tensor networks, because they have an inbuilt hierarchy in their ansatz structure. So if you look at the MPS, this is essentially a flat object, so tensors that you put on top of a lattice, whereas in this MIRA here, you see that tensors appear at different length scales, right? There's a hierarchy of tensors with one tensor on the top, right? So I will not really go too much into the details, but so what you can show is that this tensor network can reproduce a log L scaling in one dimension, which is the scaling of a critical system in one dimension, right? So this is really a tensor network ansatz designed for critical systems in one dimension. And here I can just show you some data that I borrowed from a slide from Glenn Evenbly, who has worked a lot on this MIRA here. So here you see the two-point correlation function of a critical 1D chain. And here you see a log-log plot. And here's the MIRA data. So you really see how this MIRA very nicely reproduces the power law decaying correlations here up to many, many orders of magnitude. Whereas the matrix product state, it cannot reproduce the log L entanglement scaling of a critical system, which means that eventually it will always exponentially decay. And this is what you can see here, right? So it follows the power law up to a certain distance, and then there's an exponential tail. If you increase the bond dimension, it follows it longer, and then there's an exponential decay, and so on, right? So MIRA is a more natural ansatz for critical systems, but then there's still a very important message that even though a matrix product state cannot exactly represent a critical system, it's still in practice often used. It's a very powerful tool to study critical systems because the way it approaches criticality is very systematic. So you can perform a scaling analysis and then still extract information about the critical point here. Right? I will come back to this actually later in my talk.
Hello. Why are we really worried about this? How entropy scales with area while choosing these matrix product states?
So do you mean that? So if you take a matrix product state for a 2D system, then you're limited in the system size, right? This was the message that you cannot go to arbitrary system size in 2D because the MPS doesn't reproduce the entanglement entropy. Here, in a very similar way, you can say a matrix product state due to the log L scaling of critical system, which MPS cannot reproduce, and MPS will never reproduce power law decaying correlations over arbitrary distances, but always have an exponential decay, right? So in the end, that's the limitation of the MPS, but again, in practice, you can still extract the relevant information if you know that, right? So
another quick question is that when you're choosing these matrix product states, when you're splitting this the wave function into two parts, that can be done in various different ways, right? Suppose on a one-dimensional lattice, you can split it in different ways. So why in particularly were you splitting in the middle? I mean, why can't I take some other, I can cut it from some other point?
So in the end, let me say that. So here, in the end, what the matrix product state in the end is such that it is split everywhere, right? So in the end, the matrix product state is such that every side is split, right? So this is this ansatz here. So I could have based the whole discussion based on this ansatz, but to simplify the discussion, I just considered one cut here. And so the discussion then can be, extended if you have several cuts. So that was a bit of the idea, just to simplify discussion. But here I could also have done the discussion based on cutting in somewhere else, right? So it doesn't really matter.
This is along the lines of DMRG, right? Because there also they cut along a particular edge and then they connect both the parts, right?
Yeah, so I don't know what you have in mind now. So in DMRG, there's a one variant where you also let the system size increase step by step. And then indeed, you always add sites in the middle and split it in that sense again, where you compress, right? So that's very closely related. Yeah.
Okay, thanks.
Okay, thanks. Okay, so with this, we're done with the first part. So we have seen what a tensor network ansatz is. It's a variational ansatz where the variational parameters are stored in the tensors, and then you can play around with the structure of the tensor network. And different tensor network structures in the end can reproduce a different type of entanglement scaling, and that's one way to classify them, right? So MPS can reproduce an area law in one dimension, MIRA a log L scaling in 1D, PEPS an area law in 2D. There's also 2D MIRA, which can reproduce an area law in 2D. And then there's more sophisticated tensor networks called branching MIRA, we'll not go into the details, which can also reproduce entanglement scalings beyond an area law in 2 dimensions. Right, so this was work by Glenn Evenblier and Giffre Vidal. Okay, so that's the ansatz. But of course, in a tensor network algorithm, there's more ingredient. So the next step, so we start from an ansatz, and then the next step is typically that we try to find the best possible representation or approximation of the ground state of some given Hamiltonian. Right? Imagine we are given a Hamiltonian, and then we want to find the best variational parameters to have the best possible approximation. Now, there's different methods how this can be done. So let's say there's a class of methods based on energy minimization, so where you go down in energy to try to minimize it. And then another class is based on imaginary time evolution. So I will briefly discuss that later. And then once we have found the best state, you can then probe what's the nature of the state by computing, order parameters or order correlation functions. So in order to do this, we have to contract the tensor network representing such an expectation value. And now in the case of matrix product states and the MIRA, this contraction can always be done in an exact way, whereas in PEPS, it cannot be done in an exact way, but you use approximations to do the contraction. That's another complication that we face when doing 2D calculations. So I will discuss this now in the following. Okay, so let's, in the following, I would like to tell you a bit more details about the ideas of contracting a tensor network. So how do we contract a tensor network in general? So I told you here we just take the sum of all connected indices, but in practice what we do is to contract this by a sequence of pairwise multiplications. So for example, we can start with these two tensors, multiply them together, take the next two, multiply them, take the next two, and so on until we're done, right? So then we have contracted this network. But now the thing is, we could have chosen another sequence of pairwise multiplications, right? So there's many different choices. And now the thing to realize is that the order of contraction, so the way you do it, this really matters for the computational cost, right? So whenever you contract something, you should think about what's the best way to contract it. So what is the computational cost to multiply two tensors? So it's simple if you take this example here. So essentially we take a sum over I and j, and we do it for all u, we do it for all v, and we do it for all w here. So in the end, if all these legs have a bond dimension d, then the cost will scale as d to the power of 5. So each leg that intervenes in the calculation will contribute as a factor in the computational cost. And then in practice, what we often do, instead of just taking a sum, often we reshape this into matrices. So by combining indices, so then we have a matrix multiplication, then we can call one of the high performance matrix multiplication routines, and then reshape it back into a tensor. Okay, so let's have a look at how to contract the matrix product state. So here I show you the norm of a matrix product state. So this, let's say this is the ket of the matrix product state, and this would be the bra. Right, which is typically shown as the mirror image of the ket. So we could contract this now by starting in the upper left corner and multiplying tensors together like this. But of course, this would be bad. Why is it bad? Because we create an object here which has as many legs as system size. So we would create an object which is as large as the entire Hilbert space. And that's, of course, not efficient. Okay, so the better way to do it is to start from these two tensors, take the next one, and so on. So we zip up the contraction from left to right, and then you realize you never create an object which has, a growing number of legs, right? But you can figure out that the computational cost that you have here is d to the power of 3, which is the typical cost of matrix product state algorithms. Okay, now let's have a look at contracting the PEPs, right? So here, let's say this is 3 times 3 PEPs. The ket of it here would be the bra. And then what we can do is to push these two layers on top of each other and then always multiply bra and ket tensors together. So we combine on each side bra and ket tensors, resulting in this network here, where we now have a line, a D line from the ket and a D line from the bra. And we can also combine these indices together so that we arrive at the square lattice network with bond dimension d squared between these purple tensors here, right? So if you want to contract, if you want to compute the norm of the PEPs, what you need to do is to contract such a square lattice network. So let's try to do this. So we could start here in the upper corner, multiply tensors together, and then you suddenly realize no matter how you try to contract this, you will always obtain such a tensor here, which has as many legs as the linear system size, right? So this is an exponentially large object. And this looks at first like very bad news because we have an ansatz, which is polynomial in scaling. But whenever we want to contract it, it seems we get, again, an exponential scaling in the computational cost. Okay, so this looks bad at first, but the solution is that we can use controlled and approximate contraction methods to do this contraction with a polynomial scaling in an accurate way. Now, there exist different families of contraction methods. So this is really a field of research on its own. So there's MPS, MPO-based approaches. There's this corner transfer matrix method, or the tensor renormalization group, and then the more sophisticated version is called tensor network renormalization. So there has been a lot of developments over the years how you can best contract a 2D tensor network. And now what they all have in common is that this approximate contraction is controlled by another parameter called chi, so which controls this approximate contraction. And whenever you compute something, you need to carefully check the convergence in this parameter chi. And then the computational cost is polynomial, but overall a large power in D, so roughly a D to the power of 10, let's say. So this also looks quite bad, but you have to be aware that in 2 dimensions, the bond dimensions that we need are talking about bond dimensions of maybe 4, 5, 6, or maybe 10 or 20 at most, as opposed to bond dimensions of thousands in the one-dimensional case, right? So the D here has a different meaning in 1D than in 2D. So that's why in practice, this is not such a big issue. So here I show you an example of such a contraction for the 2D Heisenberg model. So here you see the energy per site as a function of 1 over this parameter chi here for different bond dimensions. And you see here, when we go to sufficiently large chi, this has nicely converged. And especially the error that you have here is much smaller than the effect of the bond dimension itself, right? So typically you make sure that things are convergent chi and then study quantities as a function of the bond dimension. Okay, so how can we contract this network now? So one way to do it would be to use matrix product state algorithms from 1D to contract this 2D network, right? So the idea is you can see this as a matrix product state, the first top line, and the next row, you can see this as a matrix product operator. So matrix product operator has just an ingoing and outgoing leg. And then you can make use of 1D algorithms to, multiply these tensors together. and then to compress this enlarged bond dimension down to a smaller bond dimension chi, right? This is something which is often done also in 1D algorithms. And then you can proceed, you can take the next row, multiply to it, compress it until you have contracted the entire network, right? So this would be an approach how you can contract a finite PEPS. Now to contract an infinite PEPS, one of the common approaches is called the corner transfer matrix method, which I briefly want to explain here. So imagine we want to compute an expectation value here in the middle of our system, right? And then the corner transfer matrix, what it yields as an output are these so-called environment tensors surrounding the central site, right? And so given by 4 corner tensors and 4 edge tensors. Now this corner tensor here, it effectively describes the entire upper left system shown here. And this edge tensor here is this infinite column of tensors shown here and so on, right? So you try to approximate the entire 2D system surrounding the central sites using this environment tensors, which have this dimension chi here. And now the corner transfer matrix method is a way to iteratively obtain these environment tensors by letting the system grow in all directions. Okay, so let me show you here how you can let the system grow on the left side of the system, right? So the idea is that we start from an initial guess for these environment tensors, and then we insert a new column of tensors, so just a copy of these T1, A, and T3, and then we multiply this new column onto the left side, so we absorb it on the left boundary. This gives us a new left boundary with enlarged bond dimension. And in the last step, we perform a realization step where we truncate this down to chi, right? So then when we arrive here, we have a new system where the system has grown on the left by 1 column, right? So this is called the left move. And then in a very similar way, we can also do a right move, a top move, and the down move. And then we can reiterate this over and over again, and this will let the system grow in all directions. And then we can reiterate this until we have reached convergence in the quantity that we want to measure here. Okay, so this is one of the common approaches. It can also be extended, to arbitrary unit cells of our ansatz. So here would be an example of a 3x2 cell with 3x2 different tensors, or you can also really push it to very large cells. So here's an example of a unit cell with 30 tensors or 60 spin-1 half sites in this Shastry-Sutherland lattice, which we used here to determine the magnetic structure here, right? So this is really one of the big advantages of 2D tensor networks, that you can really go to very large system sizes or very large cell sizes, which is ideal if we're talking about very large magnetic structures. Okay, so these were some ideas about the contraction. So the bottom line is that in 2D, it's more complicated, but we have very controlled algorithms to do this in an approximate way. There was a question. Yes, please.
So one question that I had about the last contraction scheme is, it seems very important what ansatz you choose for the tensors that surround your initial site. So does it depend strongly on what you choose? And if yes, what is a good choice for this ansatz?
You mean for the initial guess here?
Yeah, exactly.
No, so this is in the end independent on the initial guess, right? And the trick is in the end that we have a finite correlation length in the system, and if you measure something here in the middle, then at some point you will increase the system size such that the boundary has been pushed to distances which are much further away than the correlation length, so that effectively the central site here does not feel anything from the boundary anymore. So that's why the initial guess is not really important.
But let's say we choose something very naive, like we set all these to 0 or all these to 1. We could do that, right? And you're saying that even if we do that, we would still...
Indeed,
if we set them all to 0, then the contractions that we do in the future, they will all remain 0, right?
Okay, yeah. I mean, 0 is then something, then you're just multiplying everything by 0, right? But if you would start from a random boundary, then things would be fine, for example.
Okay,
What we typically, I mean, you can find better initial guesses so that you speed up convergence, let's say, that you converge faster. But in the end, if you monitor the convergence, if you have a bad initial guess, it just means that you need more iterations in the end to converge. Yeah, but typically this is not really an issue.
Okay, thank you.
Thanks for the question. Okay, and then let me see. I also wanted to tell you a few words about the optimization. So I tried to keep this short. So one of the common ways is by imaginary time evolution. So you might have seen this already in other contexts, where the idea is that if you apply exponential of minus beta h to an initial state and take beta to infinity, that this will project you onto the ground state. Now, this is a complicated operator that we cannot directly represent, but we can approximately represent it using a Trotter-Suzuki decomposition. So where we, in the end, we write here this as a sum of, let's say, nearest neighbor terms, and then we introduce a small time step, tau, which is beta divided by n, right? As we have a small time step, and if tau is small, we can approximate the exponential of the sum by the product of exponentials, right? So this is not equal because these are non-commuting terms. So what it boils down to is that we want to apply this two-body operator onto our initial wave function between each nearest neighbor pair. This would be one time step, and then we iterate this over and over until we have reached the ground state, right? So that's a projection algorithm. So here I just show it for simplicity in one dimension. And of course, when we apply such a two-body operator onto an MPS, we want to represent the resulting state again as a matrix product state. So how can this be done? So let's have a look at one of these individual steps here. We can multiply these tensors together and then use a singular value decomposition to split these apart again. And then the bond dimension here in between will have increased. However, what we then do is to just truncate this down to the original bond dimension D again by keeping the states with largest weights, right? So that's the basic idea, and that's also called the time evolving block decimation algorithm, or TEBD. So there's a side remark here that the MPS needs to be in canonical form before you do this, but I will not go into the details here. So that's the basic idea. Now in 2 dimensions, the same applies. So we want to apply these two-body operators between each nearest neighbor pairs. However, there's now a complication that just doing an SVD type truncation is no longer optimal. And the reason is because there's loops inside the ansatz. So in 1 dimension, whenever you cut the bond, you split the wave function into 2 pieces. So you can always think of this as doing a Schmidt decomposition. In 2 dimensions, if you cut the bond, you don't split the wave function into 2 pieces because there's, other connections in your wave function. And this is why the SVD type truncation is no longer optimal. Okay, so that's one of the complications. You can still do an SVD, which gives you an approximate truncation, and it's computationally cheap, so that's the advantage. So we call it a simple update. But if you want to do a more accurate truncation after a step, then you need to use this so-called full update, where for each truncation, you actually first need to contract the 2D tensor network, which is computationally expensive. Okay, so these are the common schemes. There's also this cluster update, which is a scheme in between. And then there's progress also with doing energy minimization of the ansatz, which is actually even more accurate than doing the imaginary time evolution. So let me just show you here one example for the 2D Heisenberg model. So here you see the energy difference with respect to the extrapolated quantum Monte Carlo result. So you see here the simple update, the full update, and here, this is the energy minimization algorithm, which is even more accurate than the full update. And you see here, even so for the largest bond dimension, we obtain a value which is already very close to the extrapolated quantum Monte Carlo result, even without extrapolating here, right? So there's different optimization schemes with different pros and cons, let's say, and the energy minimization algorithms nowadays are the most accurate ones. There's also the latest progress is what's called automatic differentiation. So this is a way, so from this paper here, and this is a way how to compute gradients in an automatized fashion. So that's a technique which is commonly used in machine learning for neural networks, but has recently also been applied then to tensor networks and have become a powerful tool how to minimize the energy of a tensor network. Okay, I will not go more into the details here due to time, but this essentially completes a brief overview of the main ingredients of these tensor networks. Okay, let me get to the next part. So just very briefly, I just want to flash some things to you. So in the end, you see, I will focus on IPEPs here in 2 dimensions. There's many applications as well on the 2D DMRG side, so many groups using that approach. But IPEPs has really in the past years become a very useful tool to study 2D strongly correlated systems. So not only frustrated spin systems, but also Hubbard models, TJ models, bosonic systems, and so on. And this is an incomplete list of references here. So there's really many groups now who make very nice progress. So just to highlight a few examples, one example where IPEPs was really very useful was the study of the Shastry-Sutherland model, which is an effective model of strontium copper borate. So early on, we used this to compute the ground state phase diagram or to get an understanding of the magnetic structure if you put it in a magnetic field or in a magnetic field under the pressure here. So this will be the topic of my talk tomorrow. So we'll give you much more details about all these calculations and latest results and comparisons with experiments. But there's many more examples. So for example, that's a nice work here where they used PEPs to predict the gapless quantum spin liquid in the spin 1.5 Kagome Heisenberg model. Or that's a nice work where they looked at the double layer Kagome compound using IPEP. So using also couplings which were predicted from ab initio calculations. There's more examples for the Kagome. So here's Kagome in a magnetic field by the group of Didier Poel-Blanc, or then here a recent paper on the Kagome Heisenberg model with Dzielozinski-Maria interactions, also combined with VMC. Then examples of spin 1 cases. So we had this a few years ago, this discovery of an emergent Haldane phase in a bilinear biquadratic Heisenberg model. So that's a 1D phase, which can be adiabatically connected to coupled Haldane shades. Or that's also a nice paper on the discovery of a non-abelian chiral quantum spin liquid in a spin 1 model, or that would be the discovery of a simplex valence bond solid in a spin 1 Kagome antiferromagnet and so on. So there's really many examples, so J1, J2, or applications to Kitef Heisenberg model and so on. Another class of models where IPEPs was really useful were SUN Heisenberg models. So these can be seen as generalizations of the SU2 Heisenberg model to higher N. And so what we found here is, a very rich variety of different ground states. So generalizations, of magnetically ordered states or valence bond solids, or also quantum spin liquids here in the SU4 honeycomb case. So there's many examples, showing that IPEPs has really become a very useful tool to study these 2D systems. Okay, so that was just a brief flashing of some results. And now I would also use some time to tell you about some more recent developments. So one development is about the systematic study of critical systems using tensor networks, right? So I mentioned this already before when you try to use matrix product states to study critical systems in 1D. It cannot reproduce power law decaying correlations directly, but you always obtain a finite correlation length. But the thing is now that this finite correlation length, the way it approaches criticality is really systematic. So one idea is that instead of doing a finite size scaling analysis, what you can do is to replace your finite system size by an effective correlation length that you obtain for a given bond dimension, right? So you can take a finite size scaling ansatz and then run calculations with an infinite tensor network for different bond dimensions, and then do a scaling analysis in this effective correlation length. So that's called finite correlation length scaling. So this was all developed in one dimensions based on matrix product states. And then a few years ago, we also extended and tested this in 2D using IPEPs. And then you can really do, this data collapse plots based on finite size, which are commonly done in finite size scaling calculations to extract critical exponents and critical couplings in models. So this was an example from a TV honeycomb model. This approach can also be used to extrapolate order parameters in gapless systems, right? So here I show you the magnetization squared for the 2D Heisenberg model, where instead of plotting it as a function of 1 over the bond dimension, we plot it as a function of 1 over this effective correlation length. And by doing it this way, we can extrapolate this data much more accurately to the infinite D or infinite correlation length limit. And then here we obtained a nice agreement with the extrapolated quantum Monte Carlo result, right? So this in the end is really a useful tool, how we can extract information in gapless systems. Then I would also like to briefly tell you about finite temperature calculations with IPEPs. So there has been a lot of developments in 1D and more recently, or let's say in the past 10 years, also in 2 dimensions. And essentially one of the basic idea is that instead of representing a wave function using a tensor network, we can also represent an operator using a tensor network, right? Like, for example, a thermal density operator at some target inverse temperature beta. And then instead of having just one leg per lattice side, we now have an ingoing and outgoing leg on each lattice side. So this can be used to approximate a thermal density operator. But what we do in practice is to use this as an ansatz for the thermal density operator at beta over 2, so at half the target beta. And then you can get an approximation of rho at beta by combining this with its complex conjugate, right? So in other words, you use a bilayer ansatz for the thermal density operator, and this ansatz has the advantage that it is Hermitian by construction. If you use this approach here, you might lose this hermiticity due to truncation effects, right? Okay, and now if you use this approach, the way to obtain the representation is again by the ideas of imaginary time evolution. So same thing as we have seen before, just that the starting state now is well defined. Namely, we start at infinite temperature, where the thermal density matrix is simply given by an identity, right? So if we represent the identity by tensor network, it's simply, the initial state is simply a product of lines, so representing these identities. So here just in one dimension for simplicity. And then we can evolve this state in imaginary time. So using the same technique as I explained before for ground state calculations. So at each step, we multiply these operators onto our tensor network ansatz, and then we truncate it down back to the original bond dimension. And then we evolve up to our target beta, target temperature, inverse temperature. And then we have a representation of the thermal density operator. Well, let me just show you here some benchmark results. I will get back to this also tomorrow. So here I show you benchmark results for the Shastry-Sutherland model for the specific heat. So details don't matter too much, but here I want to show you a comparison with quantum Monte Carlo. So quantum Monte Carlo has a negative sign problem in this model, but it's weak for this coupling ratio here. And you see we obtain a good agreement with quantum Monte Carlo. However, if we go to larger coupling ratios, then you see that there's the error bars of quantum Monte Carlo explodes, right? It becomes exponentially large if you go to lower temperatures, whereas with IPEPs, we can still access this low temperature region here. And that here's a comparison of IPEPs with the experiments. So, this is effectively describing this material strontium copper borate, and we obtain here nice agreement at low temperatures. Okay, so this is, I think, a useful approach also to study finite temperature properties for models which are out of reach by quantum Monte Carlo due to the negative sign problem. Okay, and then another direction are excitations. So there has been very nice progress in the group of Frank Verstraete at the University of Ghent in formulating ways how to represent excitations on top, so low-lying excitations on top of the ground state. So they developed this for matrix product states and more recently also for PEPs. And the basic idea is the following, that you start from your tensor network representation of your ground state, and then you you exchange one of these tensors by a new tensor B, right, which carries the support of the excitation. And then you take a momentum superposition of this ansatz, so with a phase factor of IKX. So this then by construction is a state which has a well-defined momentum. And then you can optimize this tensor to obtain an ansatz for the excitation. Now, the big challenge here is that this is no longer a single tensor network, but a sum, an infinite sum over tensor networks. And the Hamiltonian itself is a sum over Hamiltonian terms. So in the end, you end up with a triple infinite sum here that you can reduce to a double infinite sum if you exploit translation invariance. And then the technical challenge is really how you can actually evaluate this, right? Do these infinite sums. Now, there's different ways how this can be done. So this has been worked out by my student, Boris Ponsiun. Another approach was also developed in Frank's group. And more recently, we also came up with a scheme based where we made use of automatic differentiation. So this is, of course, too technical. I don't want to go into the details, but in the end, here I show you some results for the low-lying excitation of the 2D Heisenberg model for different bond dimensions. So here, the gamma and x point are the gapless points. So you see, for finite bond dimension, we obtain a gap, but it's systematically approaching this gapless point here, and we can also make use of this finite correlation length extrapolations here to extrapolate this so that we correctly predict the gapless excitation here. And then more recently, this approach was also applied to this triangle lattice XXZ model with comparisons with experiments here in this paper here. Okay, and then I would also like to mention progress in 3D. So in the end, the main challenge here is to come up with a contraction algorithm to do this 3D contraction. And one way to do it is to start from a boundary PEPs and then absorb planes of PEPs onto this boundary until the 3D contraction is done. And we came up with a particular approach which essentially makes use of this simple update truncation scheme. So we split all these tensors into smaller pieces, into two-body operators that we absorb into this boundary IPEPs, so that in the end, once we have done this contraction, we are left with an effective 2D contraction. So this was developed by my student Patrick Flar. And here we performed benchmarks for the 3D Heisenberg model, where we obtained a good agreement with the quantum Monte Carlo result and also for the 3D Bose-Haber model, right? So it's, 3D tensor networks are more challenging, but I think there's really within reach and also would be a useful tool for more challenging problems in 3D. There's also a special version for layered systems, so for anisotropic 3D systems, and I will talk about this tomorrow in my talk as well. Okay, so a last word is that tensor networks are also getting increasingly important in other fields. So this is what I like about these approaches. So also in high energy physics, quantum chemistry, complex systems, nuclear physics, and so on. So that's kind of nice that these approaches find really applications in all sorts of areas. So that makes it quite exciting to work on these approaches. So with this, I would like to wrap up. So it's clear that 1D tensor networks have been the state of the art for 30 years now. So with matrix product states and DMRG, 2D tensor networks, we have seen that they're more challenging technically, but there has been a lot of progress in recent years. And particularly IPEPS has really become a powerful tool for many challenging problems. So there exist many applications already in the field of frustrated magnetism and also other fields. And I also briefly told you about new directions, new approaches to study critical systems, finite temperature, excitations, and 3D. There's other topics which I have not touched here, like time evolution or the study and classification of topological order or open systems. In the end, it's also, I think, important to realize that this is not the end of the story. So there's still big room for improvement, come up with better contraction algorithms and so on, so that we can push these methods to even higher accuracy. Right? And this brings me to the end and would like to thank you for your attention.
Thank you very much. So let's thank Philippe for this very nice and comprehensive introduction to tensor networks. And we have a few minutes for questions. Yes, please. Do you have a mic over there?
Hello. I'm audible?
Yes.
So in the Hamiltonian, we have the interaction terms, which makes it difficult to solve the quantum systems. So how does that term is actually, how does that problem is encoded in the tensor network to solve that problem?
You mean the dependency on the interactions, you mean?
Yeah, so we move from the quantum states to by truncating to such quantum states that the interaction term becomes insignificant, or what we do so that the interaction plays a role.
So in the end, you see, a priori, it's a priori really depends on the model, or let's say on the underlying ground state, which is realized, which determines how hard it is for a tensor network to represent it. And what's funny, for example, if you take fermionic systems, a free fermionic wave function is of course trivial, but it's trivial in momentum space and not in real space. So if you take a free fermionic wave function in real space, it's actually one of the cases where the area law of the entanglement entropy is violated, and where a tensor network ansatz has a hard time to represent it, right? So in the end, it really depends on the underlying state. So in that respect, the strongly interacting fermionic systems are easier to deal with tensor networks if you work in real space than weakly interacting systems, right? Which makes it also complementary to many of the weak coupling approaches. And now for spin systems, it really depends on the underlying state. But so far, there was, I would say, not really a case so far where tensor networks would come out to be too limited to represent any of these states. So there's some subtleties, maybe if you look at chiral quantum spin liquids, but there's also been quite a lot of progress in this direction. So in the end, it really depends on the underlying ground state, which is realized. And then you always have the possibility to really systematically study the state as a function of the bond dimension. So even though if you're not fully converged, maybe in the bond dimension, you can always gain information about the competing states and determine what the lowest energy state is. Of course, some cases are harder than the others, but that's how it is, yeah.
Thank you.
Thanks.
All right, further questions?
Hello? Does it work now? Oh yeah, now it works. So I was wondering about the validity of using IPEPS for finite temperature, because initially the idea is that you only have a tiny portion of the Hilbert space which you actually represent, right? And that is close to the ground state, but at finite temperature that doesn't work anymore. So could you maybe explain again why that even works?
So in the end, you see, for finite temperature, we don't use a wave function to capture the states, but we directly represent a density operator, right? So And the thing is now one can show that these finite temperature states obey kind of the analog of the area law of the entanglement entropy for mixed states, namely an area law of the mutual information. And this can be shown is also reproduced by a 2D PEPS ansatz. So in that sense, so the analog is a bit that, you know, a 2D PEPS ansatz for a density operator, so with, you know, not the wave function, but with ingoing and outgoing legs, reproduces an area law for the mutual information that the typical finite temperature states obey, and that's then the kind of motivation to use this as an ansatz. I mean, in the end of the day, it does not tell you what you can expect in terms of accuracy. You know, are the bond dimensions that we are able to achieve sufficiently large that we can get a sufficiently good result at finite temperature? But because it's systematic, we can always check what happens as we increase the bond dimension. And if we converge in the bond dimension, then we have some certainty that things are fine. But for example, at finite temperature, in some cases, we're still limited in the temperatures that we can reach. So high temperatures are easy, but then there's an intermediate temperature regime, which is still difficult, right? So in the end, it's still not so much explored what's the, you know, how far we can actually push this. Yeah.
Okay, thank you.
Thanks.
We have a question from the online participants. Please unmute yourself.
Yeah. Can you hear me?
Yes.
So I have a question about evolving the system with a total decomposition. There, with the decomposition, you may have some errors. So what is how much can be trustworthy? Like how can I control the error, and then how much can be feasible, like for the results?
Mm-hmm. So in the end, of course, we introduce an error here, but we can use a higher order scheme than just this simple as a higher order scheme, such that the error, the Trotter error, is really reduced to something small. So we can check also different values of tau to see what the effect of this error is. But in the end of the day, the dominant error typically in these calculations is really the truncation and not the Trotter error. So this is why typically we don't worry too much about the Trotter error. Of course, if you really would go to high precision calculations where the truncation does not matter so much anymore, then you need to be more careful about the Trotter error as well. But in principle, you know, this can be probed in a very similar way as in other approaches, like in quantum Monte Carlo, which, I mean, for those which are also based on a Trotter-Suzuki decomposition. Yeah. Does this answer your question?
Yes. Yeah. Thank you.
Thanks.
Okay. Any additional questions?
I had one question. So you mentioned the other method, MERA, right? I was wondering, do IMPS and IPEPs have some advantages over MERA in 1 dimension and 2 dimension?
Yeah, you see, so the MERA is a very natural ansatz for critical systems, but the scaling of the computational cost is typically considerably larger than with matrix product state. So there's really a trade-off, right? It's a more natural ansatz, but the algorithms themselves come with a larger computational scaling. So it's, I think, chi to the power of 7 or 8, as opposed to the power of 3 for matrix product state algorithms. So in the end, you know, as a practical tool, in the end, people still would then use matrix product states instead of the MERA. And in 2 dimensions, things are even more extreme. So the 2D MERA comes with a very high power in the bond dimension, the algorithm, such that it's difficult to be competitive with PEPs, for example. Right, so it's, you know, it's a very nice ansatz, but then on the practical side, it's a bit more involved and computationally more expensive.
Thank you.
Thanks.